All right, you guys. So we did binomial, which means that you had to have bins in order to do anything binomial. And for bins, it had to be binary, independent, a fixed number of trials, and a fixed probability of success every time. Okay? So now we have what's called a geometric random variable. Write that down. Okay? Geometric has everything the same as binomial except you play until you win, or you keep going until you get a success. So n is no longer a fixed number of trials. So you're going to roll the die until you get what you determined was a success. Or you're going to shoot a basketball until you get a three-point shot. Or you're going to play Russian roulette until you win. All right? These are all examples of geometric settings. So the shortcut for this one is bits with a T. So still binary, still has to be independent, but instead of a fixed number of trials, the T means until. I don't know why, just does. Okay, until. Play until you win. NS is still your fixed probability of success. So is this your lucky day? We're going to play a little game that involves your homework and the number of problems that you're going to have tonight. All right? This is not rigged. This is not rigged. The last one was rigged. All right. So this one's not rigged. So what's going to happen is they're going to say day of the week. We're just going to say the numbers 1 through 7. It's the same thing. There are 7 days in the week, okay? And what happens is you're going to guess a number, 1 through 7, and I'm going to do a random number generator. And if it matches on the first try, you have only one homework problem. Okay? And then my number changes every time because the probability has to be 1/7 every single time. So you guys get a pick again, okay, on another number. And then I do random number generator, 1 through 7, and we see if it matches. And if it does, we stop playing the game and you only have 2 homework problems, right? So we're going to do this until somebody wins and gets a match, okay? So do you guys want to play? Yeah, you want to play? So let's check bits for this. The game we just played, right? So is it geometric? That's what we're asking ourselves. So the first one, the B, Matt H, what's the B stand for? Binary. And so Matt H, is it binary? What is defined as success in this problem? Getting it right? Yeah. So you either guess right or for failure, you guess wrong. Okay. And Grace, what's the I stand for? All right, so does one person's guess affect the others? Is it independent? Yeah. Okay. And April, the new one on this, what's the T stand for? Until. Did we play until we won? And Haley, what's the S stand for? Probability of success. So P, what's the probability of success every time you play? Yep. Every time. So let's write the formula down first because that's important. So the geometric probability formula is the probability that y equals k. Y is whatever you define your random variable as. You should write this down, Charles. And 1 minus p, that's the probability of failure. You always put the probability of failure first because you're going to fail and fail and fail and fail until you win. Right? So the p is the probability of success. And the 1 minus p is the probability of failing, right? This k is the number of times that it takes here. So the last one, the exponent is always a 1. Because once you win, you stop playing, right? So once you get a win, you're done. Which means that this part is k minus 1. So it's the number of times it's going to take that we fail that goes right here. So same game here. Let the random variable y be defined as in the previous example. My mouse went away. Or else I would, there we go. All right. Find the probability that the class receives exactly 10 homework problems as a result of playing the Lucky Day game. So we used y for our random variable. So the probability that y equals 10. So we're using our formula for this. And yes, we have a calculator function. We'll get to that, Grant. So the probability of failing, the probability of failing, you guys, is what in this game? Yeah, we win 1 out of 7 times. We lose 6 out of 7 times. So if we want to win on the 10th try, how many times do we have to lose? That is the exponent that goes here. 9. How many times you failed? And then the probability of succeeding is 1/7. And it will always be a 1 because you stop playing after you succeed. And these have to add to 10. All right? Plug that into your calculator. It's like 0.115 or something. All right, whatever that is. And part B. Find the probability that y is less than 10 and interpret this value in context. What does it mean for it to be less than 10? Alexis, what do you think? But in the context of this setting, when we're playing the game, so getting it on either the 9th time, the 8th time, the 7th, right? All the way down to the first try, okay? So this would be the probability that you got it on the first try, plus the probability that you could get it on the second try, plus the probability you could get it on the third try, plus the probability you could get it on the 9th try, right? Each one of these is a formula, right? Every single one you have to plug in a formula. So let's do one for getting it on the first try. So you always do the probability of failure first, which is 6/7. If you get it on the first try, do you ever fail? No. So what exponent goes here? 0. All right. And then our probability of succeeding is 1/7. And that has to happen. There's always a 1. We stop playing. These have to add to 1. All right. Plus, now let's do the probability we get it on the second try. So, Pete, what goes first? 6/7. How many times are we going to fail if we get it right on the second try? Yep. And Haley, what goes next? And that's always going to be to the first power. All right. And let's do the third one. Tori, what goes first? Close. How many times are we going to fail? Yep. We're only going to fail twice if we get it right on the third try. And then you can do ... and let's do the 9th one. And so, Alexis, what goes first? Okay, if we get it on the 9th try, Charles, what exponent goes here? Good. And Pat, what goes here? Yep. Add all those up. Okay, you'd plug that all in, and you'd get your probability. And I should probably... So this one's 0.036, so pretty small percentage chance that you guys would have gotten it right on the 10th try. 9 or less is actually 0.75, so that's a pretty good chance that you guys would have had less than 10 homework problems. So you made the right choice in playing the Lucky Day game. All right. So of course we can do these on our calculator, because everything can be done in our calculator and stats. All right. So geometric PDF. What do you guys think the PDF goes with? That's when it's exactly one thing. I want to get it right on the 5th try. I want to get it right on the 3rd try, right? What's the CDF? Anybody? CDF? What we just did, like less than 10, okay? Any kind of range of answers, greater than, less than, okay? So go to menu, statistics, distributions, and go ahead and find geometric PDF. Everybody go to PDF first. And Pete, did you find yours? Okay. All right, so let's do this first one. And again, when you use this function, and you're going to use both on your 3 homework problems tonight, you got to show both, okay? So I'm going to do geometric PDF. And if you have the Inspire, what does it ask for first, you guys? Probability of success. In this game, what's the probability of success? All right, and then what does it ask for? Oh, I should have put a P here, you guys. Got to label these. X value. What do you think we're going to put in for X value? Yeah, we want to get it on the 10th try. So you plug in 1/7 for the probability, X value of 10, and you get 0.036, hopefully. Everybody check that. They got that on their calculator. Please plug this in and check it. All right, and now let's do the less than 10, okay, within, 9 or less here. So for this one, we're going to do geometric what? Yeah, CDF. So what does it ask for first? Probability. What do we plug in? You guys all go to this. Here, 1/7. I'll just pause. And then what does it say? Lower bound? 1. In this case, 1, because we have to actually play the game. Sometimes it is 0. You got to think about it. What's our upper bound? 9, because we want less than 10. Okay, and hopefully you get the same answer. Now, if you have the 84, you don't get lower bound, upper bound. You only get a plug-in upper bound, which means that yours only do less thans. All right, they only do less thans. If you're going to do a greater than, what are you going to have to do? 1 minus. So you'll always subtract from the less than. So you got to think opposite and then do 1 minus. Okay. This one was less than, so you just plug in 9. 1/7 and 9. You can't do 10. You have a 10 in there. We also have an expected value or a mean for our geometric random variable. So again, binomial was n times p. But for geometric, this is the mean or expected value. So mu of y or e of y. So mean is the first part, expected value is the second part, is 1 over p. Easy formula, but easy to forget. Don't forget it. All right, 1 over p. What do you guys think p is? Probability of success. So for the last problem we were just doing, it would be 1 divided by 1/7, which is 7. What does this mean? After playing many, many times, right, this lovely game, you would expect to get how many homework problems? 7, because you'd expect to get it on the 7th try. So you guys did better than the mean. Good for you. Okay. So, let's see if we got this. Suppose you roll a pair of fair 6-sided die until you get doubles. Let t equal the number of rolls it takes. Show that t is a geometric random variable. So, Pat, what do I do to show t is a geometric random variable? What's the little, yeah, we do bits. Okay, Grant, what's the B stand for? So is it binary? Yep, you either get doubles or you don't. Okay, Matt in, is it independent? Yep, when you roll one set of die, it doesn't really matter, doesn't affect the next one. Okay, and Melissa, what's the T stand for? Yeah, so are we playing until we win? Yep, and Claire, what's the S stand for? So what's probability of success? You guys know this. Actually, we probably should talk about this. They didn't give it to us. So rolling doubles, you could just like make your little chart, right? Some of you guys already know it. Good. And then you count up all the doubles out of 36, and it reduces to 1/6. All right. So your probability of success of getting doubles is actually 1/6. Find the probability that t equals equals 3 and then interpret this in context. Let's talk about interpreting it first. So, Samantha, what does the probability that t equals 3 mean in context here? Not 3 times, but there you go, on the third try. Okay, so you don't get doubles, and then you get doubles. So let's do the formula. So the probability that t equals 3. And so if it's a 1/6 of success, Patty, what's the probability of failure? Yep. And Kelly, how many times are we going to fail here? Yep. And then Bert, what's the probability of success? Good. And that's always a 1. Okay. Plug that in and you get 0.11. So there's like a 12-ish, 11, 12-ish % chance that you're going to get doubles on the third roll. All right. In the game of Monopoly, a player can get out of jail free by rolling doubles within 3 turns. Find the probability this happens. So the probability that we get doubles within 3 turns. So that means we could get it on the first try plus the second try or the third try, right? So let's say we want to get it on the first try. So Kenny, what's the probability of failing if we get it on the first? Well, what's the probability of failing anyways? Right, and what power is that going to be if we get it on the first try? Yep. And that means we have a 1/6 to the first. And now we've got the second try. So Charles, what's the probability of failing? And how many times that can happen? All right, and that means we succeed once, right? And then it's going to go 5/6 to the second, ran out of room here, and 1/6 to the first for that last part. Add all those up, 42% chance you're going to roll doubles within the first 3 turns, okay? We can also use our calculators. Let's say we're using our calculators for this, you guys. Is it geometric PDF or CDF? CDF. Be sure you always label all your stuff. What was the first thing our calculators asked for? P. What's the probability of succeeding? 1/6. Okay, for CDF, we have a lower and an upper. What's our lower bound? We got to play, so 1. And upper, 3. Okay? I will figure out your 3 homework.